Welcome back, pre-calc honor students. Mr. Sarko in the house for some 11.8 action. All right, this one should be pretty short and sweet. We're talking about the probability of independent and dependent events. All right, so before we go on, I want to talk about what these two words mean. All right, so think about what it means to be independent and what it means to be dependent. All right, so independent, of course, means on its own, doesn't rely on anyone or anything. Dependent, the key one, this one definitely relies on previous events in real life. Most of you, if not all of you, are dependents, right? You depend on somebody to buy your food, clothes. As much as some of you want to try to say you're grown, right? You still don't live alone. You don't work. You don't make your own money. In a essence, where you can really run things, right? We're all, at least till we kind of get to be 18, usually we're dependent on somebody, right? So whether it's dependent or independent, what we're going to do to find our answers is we're going to find the probability of these events, and we're going to go ahead and multiply them. Right, so the key word here that I want you to focus on is and. When you see and, this is a telltale sign that we're going to multiply. All right, we'll talk about or in a different section, but when you see and, I want you thinking multiply. So example A, find the probability of getting a 3 on each of 2 throws of a die. Well, we kind of did this actually in our one of our previous sections when we made the chart with the dice. Okay, well, think about it. What's the probability of throwing a die and getting a 3? 1 out of 6. What's the probability of picking that same die up, throwing it again, getting a 3? 1 out of 6. So the likelihood of throwing a die twice and getting a 3 each time is 1 out of 36. Okay, now you could go the decimal representation as well. Nice easy ones like 1 over 36, I prefer to 0.0277, especially I want to eliminate all rounding if at all possible, because then it changes our probability subtly. The probability 0.027 is significantly different of 0.0277, especially when we're talking about wide scale things, big amounts of events happening. All right. Find the probability of getting the sum of 2 on the first roll and a sum of 3 on the second roll of 2 dice. So here's what I want first. That's what I want second. I'd recommend going to your little chart that we made. I don't remember exactly what section it was, 14.4 maybe. Looking at that chart or in your worksheet packet that's provided to you. In order to get a sum of 2, all right, the only way that happens is a 1 and a 1. In that chart, this is a 1 out of 36 likelihood. Now, to get a sum of 3, okay, if you look at that chart, you can get a 1 and a 1, a 1 and a 2, and a 2 and a 1. That's 2 out of 36. And now we multiply those out, and we get 2 over 1296, which simplifies to 1 over 648. All right. You could also say 0.0015. Again, I tend to want to stick to the fractions if at all possible. Clean that one up a little bit. All right. Personal preference, like I said, I like the fractions better. Now we'll go ahead down to dependent events. Dependent events, like I kind of said earlier, the outcome of the first selection has an effect on the second selection. So to kind of compare it to the ones we just did, we roll a die, whatever we get, we erase that number, right? You can't really do it for a die. That's why we tend to do a lot of decks of cards when we're doing things that are dependent, because you could imagine holding a deck of cards, pulling out a card, keeping it, now you have less cards in the deck. That doesn't quite work the same when you flip a coin or roll a die, because the numbers are always there, the heads or the tails is always there. If you're not super familiar with a deck of cards, right, there are 52 cards in it. There are 4 suits, diamonds, hearts, spades, and clubs. There's 13 in each suit, 13 in each, and there is 4 of each card. You can go 2, 3, 4, blah, 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 10, jack, queen, king, ace. So there's 13 cards, 2 through ace. Each one of them has 4, 1 of each suit. You can always just search this online. You can Google deck of cards to see what that looks like. Now that we're all quarantined, it might be a good time to start playing some cards. Ask your parents. Cards is a little bit of a lost art now. Not that many people play cards like they used to. So it could be fun to learn how to play some games, spades, hearts, poker, etc., and learn a little bit about a deck of cards. But so here, find the probability of getting 2 hearts from a deck of cards. All right. So when you're thinking about that, it doesn't say pick a card, put it back in the deck, draw another card. It just says drawing 2 hearts, which means I'm taking 2 cards. Well, there are 13 hearts out of a 52 card deck, right? The top number represents hearts. The bottom number represents total. So there's my first. Now, I'm going to multiply that by the resulting amount. Okay, so I've drawn a card. I've taken 1 heart out of the deck, so how many hearts are now left? 12. How many total cards are left? 51. Now we're going to go ahead and multiply those 2 numbers. You get 156 over 2,652. Always simplify if at all possible. That's a 1 over 17 chance, which if you're someone that likes the decimals, I show them to you just to have it. But I always like that fraction, like I said the other times. Okay, so again, dependent means I want to get 2 hearts. That means I draw a card. There's 1 less card in the deck and 1 less heart in the deck. So now my probability changes from that first card, 13 out of 52. Alrighty. And last but not least, there are 6 red, 2 blue, and 9 black marbles in a bag. First thing we should do right here is get a total. How many total marbles? There are 17 marbles. 3 marbles are chosen without replacement. Actually, let me do this. Let me highlight it. What does without replacement mean? All right. Without replacement, of course, means I'm going to draw a marble and I'm going to keep it. If I said with replacement, now these events are no longer dependent because I'm going back to the original start. So find the probability of selecting a red marble. Well, there are 6 red out of 17 total. Now I want the probability of a blue one. Well, there are 2 blue, but how many marbles are still in our bag? Remember, we took a red one out and didn't put it back. So now we're down to 16. And then, hey, I want my third one to be a red. Well, we started with 6 red, but remember we pulled one of them out. So now we're down to 5 reds, and we have a total of 15 marbles now. So look at the top numbers. Before I multiply these out, 6 out of 17 represented the original 6 marbles that were red out of the total of 17. You take that out. You put it to the side. You put it in your pocket. Doesn't matter. Now I want a blue one. There's 2 blue, but only 16 marbles left due to the red that we took out. Now I go back to red. Well, we lost a red and we lost a blue. The red affects our top number 5, and the blue and the red missing affect our bottom number, which was 17, now is 15. Okay. You could do some cross-canceling here. The middle blue fraction could become 1/8 times 1/3 if you want to do that. If you have a calculator, it's not bad to just multiply the top, 60, multiply the bottom, 4,080. All right, go ahead and simplify that down to 1 over 68, which for all you decimal people out there is 0.0147. Remember, if this was a no calculator question, I'd simplify 2 over 16 to 1/8, 5 over 15 to 1/3. Then, well, let me just show it just for fun. If this was no calc, I'd go 2 over 16 becomes 1 over 8, 5 over 15 becomes 1/3. All right, then I would go ahead and do 6 over 3 becomes a 1 on the bottom and a 2 on top. Now, if I'm looking at this, it's not that bad to see on top I have 2, on the bottom I have 17 times 8. Oh, well, hey, I can do something with that. That's a 1. That's a 4. That gives me 1 over, and 17 times 4 really isn't bad. That's going to be 40 plus 28 for 68. Right, so I got the same answer, no calc compared to calc. Obviously, in this class, we should always be prepared for a no calculator portion. That's how I would do it without a calc. So without further ado, that completes 11.8. Again, let us know if you have any questions, comments, or concerns, and thanks for tuning in.